So this is the CoCalc thing. I think it's like $5 a month to get access to this browser-based CoCalc. If you don't want to do that, then I think SageMath.org. Let's see. Yeah. So first of all, you can use, I guess, SageMath Cell, but you can download this. Just install 9.8, and then it runs on your computer for free, the full version. Okay. And alternatively, you can sign up for CoCalc and buy like a $5 a month subscription if you don't like installing things and making them work on your computer. And I don't know what SageMath Cell is. Maybe like you can just make little calculations. But what happens if you try to? Well, anyway, you can do evaluate and it gives you 4. But anyway, what I want to show is some basic plotting. So I'm going to create a Sage worksheet, which you can do on your computer if you download SageMath. And let's say plotting tutorial. I'm just going to show you all the ways to plot stuff. Okay. So I'm going to zoom in, and in the Sage worksheet, you should have some drop-down menus, and there's one for plots. So you can do 2D plotting, and if you click any one of these, it'll give you an example, and you can hold Shift-Enter, and it'll do it for you. So this will plot a single variable calculus function, and yeah, and then you can change it and adapt it to whatever you need. Let me get rid of it. And I'll go to plots, and what's a line? So I just say Shift-Enter. Okay, now I see how to make a line. I make a list of 4 points, and it makes line segments that connect those 4 points into 3 segments. Okay, and that's good. Now what you can do here is you can name this thing whatever you want. I usually name my plots PLT, or you can name them Alex. To make an empty one, you say graphics open parentheses and call it PLT, and then you can add this line plot to it. And it won't display now, but if I then type PLT, it'll display. And now if I want to add some more things to this plot, like my function, then I can say PLT plus equals, and then display it, and it should give, yeah, so now it has both. And so this is nice because graphics objects can be added together. So that's a nice feature of Sage that makes plotting easy. Let's look at some other things that we can do. Plots 2D parametric. So this will be useful. So I'm going to add this to our plot. And now you see it's got this interesting loopy star. And you can see what it does. It has a function here of x, and then a comma, and then another function. And then it says x goes from 0 to 8 pi. And so now I'm parameterizing by some variable, and I give 2 component functions, which will give me a curve in terms of that one variable. And that's a parametric plot, which you'll read about in chapter 1. What else can I do? Plots, points. Okay. So this time it wrapped it in a show command. I'm going to get rid of that because I want to add it to my plot, and I have to get rid of that last thing. And then, oh, aspect ratio equals 1. Maybe I should remember that. Can I put it? Plot dot tab, and then I think there should be aspect ratio somewhere. Set aspect ratio. And now I do the parentheses and then tab to see what I need to tell it to set the aspect ratio to 1, in case it's not already 1. So self is, you ignore that. It just takes one argument, ratio, a positive real number. And so the examples, it just puts 1 right there. So let's do that. Why not? And then I get some points. Now it added some points there. I can add another one. How about 4, 4, comma. And you see there's my new point. So that's good. what else can I add to plot? Plus equals two-dimensional polygon. Okay, maybe I'll skip that one. Random walk text. Oh, text, that's kind of fun. What does that do? Oh, you can do it even diagonal, and then you can type LaTeX in there, and it'll make it look all nice. That's super useful. And you can rotate it too, and you place it at 1, 1. So I think it's probably centered at this point here. Anyway, so I don't know any of this. I'm just figuring it out as I go, and that's how you should approach coding. You don't need to understand it. You just need to make it work. Okay, let's get rid of that. Now let's do three-dimensional plots. I'll just go through all of them. Oh, torus. Shift-Enter. There we get a torus. That's kind of fun. Inner radius, outer radius. What if I do 2 and 3? What does that look like? Oh, I wonder what the inner radius 1. So inner radius must be like the width of the torus, like the circle that goes around. I don't know how to say it, but you play with it and you figure out what's going on. There's a spin. I can set that to 0 because it's sort of annoying. Then I can spin it if I want to. Okay. And the same thing, they wrap this in a show command, but I can get rid of that and then give it a name like PLT. Then if I want to look at PLT, I can look at it. Okay, let's what's another 3D plot? Function. Okay. So I'm going to add this to my PLT and see what I get. Oh, okay. So now I have some kind of function. This is a function of x and y, where the third dimension is used to graph the to put the value of the function. So that's typically not what we want, actually, but that's fine. Let's look at three-dimensional icosahedron. Again, it wrapped it in a show command. We can get rid of that and just add it to our plot and display it. And where's the icosahedron? Oh, there it is, in the center. You can zoom in. Wow, that looks kind of fun. This is a torus. At the center is an icosahedron. Wow. This is great. I don't know, something about plotting things is always fun. Implicit plot. This will be really useful. Implicit plot, parametric curve, parametric surface. Those will be very useful. Okay. What, do we miss an implicit? They didn't have one in the 2D, but they do. You can do it. So anyway, let's get an implicit plot going. So it makes some variables. There's several ways to do this. This is apparently one of them. There's like literally 8 different equivalent ways to declare symbolic variables. Then you can use them to make functions and polynomials and stuff. Here we see that you can, if you put a plus, you can continue typing on the next line. That's kind of nice when you have long formulas. They're wrapped in a show command, so I'm going to get rid of that. PLT plus equals. And I'm going to get rid of the outer. This was part of the show command, so I get rid of that. If I end this line on a comma, I can continue typing on the next line, which is nice. So let's do that, and let's display. Wow, this is interesting. And still, inside of here should be our icosahedron somewhere. It's hard to see. Anyway, this is why I like SageMath. It's so easy to get really nice interactive visuals. And then if I want to submit this, I take a screenshot. And I put it in my LaTeX file as a like a .png, something very low resolution so that the file doesn't get big. But okay, so now how does this implicit plot 3D work? Well, you need to give something called P, which I look up here and it looks like a function of 3 variables. Okay, so implicitly, we are setting p equal to 0. This function already does that, so you don't need to type equal to 0. If you wanted p equal to 1, then you'd need to subtract 1 from p, so that when the computer sets it equal to 0, the 1 can move to the other side and you get equal to 1. Pause the video if you don't understand what I said. If I wanted p equals 1 plotted, then I need to put a -1 in this. Okay, because this command will just plot p equals 0. Then I need to tell it, what is the range in space I want to plot. And so they define little r as 4.77. They defined little g as the golden ratio, which apparently Sage just knows. And then they used little g in their definition of this function. And then they used little r in the command implicit plot. Okay, now let's just real quickly, I'll show you that implicit plot also works in 2D. And so I'm going to press tab, and I see how to do this. I need f, and plots the curve f of xy equals 0 over the specified x range, y range. And then I can get examples down here if you scroll down long enough. Here we go. So I'm just going to copy all that Sage stuff. I can type escape to get out of there. Paste. Now will it even... Yeah, so I just need to get rid of all this Sage : stuff that was messing up. I don't know about this. I'm just going to get rid of it. See, here's another way to declare the symbolic variables x and y. Apparently you can just do this. And I don't need to understand what you can do, because I just type enter. Oh, interesting. It printed out that I've declared these variables. What if I do like semicolon at the end? Will it not print it out? No, it still printed it out. All right, whatever. But you see, I get the implicit plot of this circle. That's useful. To get a parametric plot of a circle, I'm going to do a list of 2 functions, and I'm going to use the variable t from 0 to 2 times pi. And my variable t will go into these 2 coordinate functions, cos t, sin t. And let's make this color equals red. Oh, it's an error. T is not defined. So I need a variable t. So I'll just add it up there. Did it work? Yeah, okay, there's the circle. And why don't I just do 1.1 times cos of t. And I'll call this PLT, and then I'll add this to PLT, and then it won't display it, so I got to type PLT. And now we see a small, this original circle had radius square root of 2. So let's put them, there we go. Okay, so I made a slightly elliptical circle. In other words, I made an ellipse in red and a circle in blue. And so you see, if I got rid of this 1.1, then they would just be on top of each other and look like a pink because the blue and red clash or combine. That's interesting. Okay, so that's kind of fun to do. So implicit plots and parametric plots are the main 2 things that you'll need. Sometimes you'll want a graph. Graphs are a special case of parametric plots. So why am I saying that? Because let's say I wanted to graph y equals x squared, or the function f of x equals x squared. I could do that as a parametric plot where my 2 functions are t and t squared. So I just put f of t in the second slot and t in the first, and then it's the graph. So graphs are a special case of parametric plots. But parametric plots are more general because graphs have to pass the vertical line test. And so that puts a lot of restrictions on what is a graph. The implicit function theorem says locally everything is a graph. At any point, one of the partials will not be non-zero, and that's the one, that's the variable you can solve, quote, solve for, end quote. Okay, anyway. So I did implicit plot in 3D as well. And then we can do a parametric plus equals parametric plot 3D. And if I want an example of that, I can just go up to plots 3D parametric curve. How about parametric curve? So here I only have one variable, so I'll get a curve. It's a one-dimensional manifold. And I need 3 coordinate functions because I'm in 3D. So I'll do plt plus equals. And then I'll plot. And where's my curve? Do you see it? Oh, I see it. It's in green. Let me zoom in. See, it's that helix there. I don't know if you, yeah, there it is. You can see this green helix. It's very hard to see, actually. Why don't I make it thicker? So thickness equals 5. How about 50? Now let's see if we can see the helix. It's not much thicker. That's disappointing. So sometimes things don't work great, but you do what you can. Yeah, it's still hard to see the helix. Anyway, I don't know why thickness isn't working. Let's add a parametric surface. Plus equals parametric. How do I do parametric surface? I bet it's the same, parametric plot 3D, except I specify a second variable. So instead of just u, see, I just copied and pasted the parametric curve, and now I'm just gonna add in another variable. How about x from 0 to 1? And then I'll just throw in some x's into these coordinate functions. And I have no idea. This might be a terrible surface. Let's look at it. Ah, there it is. Interesting. It's like a, I don't know what it is. Well, you can play with this. You can calculate the Gaussian curvature of this surface if you so desire. Okay, so that's parametric, implicit. We saw how to do points. Well, no, we didn't see how to do points really. So let's take PTS equals a list. How about 1, 1, 0, 2, 2, 2, and then let's say 4 point in points colon PLT plus equals point of point. So here's, let's create a new graphics object to sort of clear everything, and then let's display it. So here I have 2 points. See, one is at the top corner. Okay, let's make them bigger. Size equals 50. There we go. Now you can see my 2 points. And so this is a nice way to display a bunch of points. You can just say point of, and then that thing. The last thing I'll show you is that, so if I take these things here, like 1, 1, 0, 2, 2, 2, and I try to add them together. Let's see what happens. So you see, if I add these things together, it just concatenates them. It makes them into a longer list. This is called a tuple. So that's not what we want. If we want these to be viewed as vectors, that's not what we want. So you could say, oh, maybe I have to put them in square brackets. Now what will plus do? Same thing. It just makes it longer. So that's why it's really useful. And this is like, so SageMath is basically Python, but with some extra stuff added on. If I make these lists into vectors, then I can add them, and they now add in the usual way. I can even linearly combine them by scaling them before adding them, and that's super useful. I can give them a name, 1, 1, 0, and then I'll say, how about norm of W, and it'll calculate the norm. So it knows all sorts of things. Once you declare, once the computer knows what W is, then you can, and the computer has to know, Then you can type w dot tab and see what stuff you can do with it. Okay, so you can see what its base string is, the integer ring. Okay, so if I make it into a 1.2, now I look at the base string. The base string is a real field with 53 bits of precision. So these are floating points. I wonder if I do like 1/2. Base string is a rational field. So it sort of automatically tries to pick a suitable base string for you. You can look at other stuff, tab, coefficients. I don't know what that'll do. Okay, supposedly that's the coefficients. So anyway, that's a nice thing. Derivative, what does that mean? Error. No differentiation variable specified. When you get an error, usually look at the very end. Ignore all this stuff. At least I do. Okay, so how about I'll differentiate with respect to x. Error. A Sage ring's integer has no attribute derivative. Okay, so if I make a variable, I think x is already a variable, but and then I put a variable into this vector. Now let's see what the base ring is. It's a symbolic ring. So now I can do the derivative, and it takes the derivative of each component. So this is like the derivative of a curve. Section 2.1 of Lang's calculus book. Okay, so I hope that was useful. Vectors, points, plotting, this should get you started.